Okay, only one last problem remaining in chapter 5. So in examples 1 and 2, all right, settle down everyone, please. Okay, in examples 1 and 2, we saw how we can combine sinusoidal voltages, right? Multiple components added together. Examples 3 and 4, we saw how we can apply Ohm's law to circuits containing inductors and capacitors to find the voltage and the current. Now we will apply the same techniques to a RLC circuit. So in example 5, we have a resistor, inductor, and capacitor all in one. We are asked to find the total current through the circuit I of t, right? I of t, as you can see, is the same current that's flowing through all components. And we're also asked to find VR, VC, and VL. Okay, VR, VC, and VL. Now, what is the first thing that strikes you in here? What is the connection between all 4 components? They're in series, right? So they share the same current, I of t. Now, the first thing that always tells students to do when you're solving for AC circuits is to draw out the equivalent impedance diagram. Okay, equivalent impedance diagram. And what I mean is you will replace all the components in there with its complex counterpart, meaning represent everything with complex numbers, right? So voltage Vs will be represented with a phasor of Vs. The resistor, inductor, and capacitor will be represented with their respective impedances. So once we do that, you would get a circuit diagram that looks like this. Resistor impedance is the same as the resistance, so R of 100 ohms. Inductor is replaced with its impedance ZL. Capacitor is replaced with its impedance ZC. So now, if you don't look at the notations, what do we see? We see 3 resistors all connected in series. And if you think back to chapter 2, this is something that you have already done, right? Chapters 1 and 2, this is something you've already done. Applied Ohm's law, KCL, KVL, resistive circuit analysis, reducing a large network of resistors down to one single resistor and simplifying from that point on. And so that is exactly what we're going to do, except the math is now with complex numbers. That's the only difference. Okay. So I know ZEQ. Well, I'm going to reduce this to ZEQ. So this circuit becomes like this. Voltage source, one single impedance, and the ZEQ is equal to R plus ZL plus ZC. Vs divided by ZEQ from Ohm's law gives us the phasor current. That's it, as easy as that. So first step, extract as much information as we can. When we equate Vs of t with the standard expression for a sinusoidal waveform, I can obtain the magnitude Vm, which is 100 volts. I can obtain omega, which is 500 radians per second. And I can obtain the phase theta, which is 30 degrees. And the phasor for Vs is simply magnitude 100 and phase angle 30 degrees. For ZEQ, I need R, ZL, and ZC. R, of course, remains the same. ZL is J omega L. Now, ZL in rectangular coordinates is J omega L. In polar coordinates, it is omega L with a phase angle of 90 degrees. Early on, I developed the habit of calculating both polar as well as rectangular coordinates at the same time, because I never know how the problem is going to turn out, and I might need it somewhere down the line. In this case, I need to find ZEQ, meaning I need to add all three of them together. And again, repeating myself, my calculator cannot add two complex numbers if they are not in rectangular coordinates. So I need a rectangular coordinates. But then later on in this problem, I'm going to apply Ohm's law again. I need to find VR, VC, and VL. For VC and VL, I would simply take the current I, multiply it with ZL and ZC. So I need to multiply two complex numbers. And again, I need to have them in polar coordinates for that. So I try to find both at the same time at the beginning of the problem. You don't have to do so if you don't wish to. You can have the answer either in polar coordinates or in rectangular coordinates. Either one is fine. ZL is 0.3. So I get J 150 ohms. In polar coordinates, it is omega L with an angle of 90 degrees. So it's 150 with an angle of 90. ZC similarly is 1 over J omega C. There, all of them. So total ZEQ is simply 100 plus J 150 minus J 50. And then since I need to divide, I'm going to find the polar coordinates. Now, while you are solving problems in class, this is a good opportunity for every one of you to practice. So if you have your calculators, I would recommend that you take them out and go through the exact same steps. See if you can go from here to here. See if you get the exact same answer. You should. I mean, there's no reason why you shouldn't. Yes? Okay. You don't have to convert this or have this answer in polar form. Okay, you can keep this 100 plus J100. You can have Vs divided by 100 plus J100. Again, it's my calculator that cannot do that function. That's why I have the answer in polar form. Do you obtain this exact answer? Right, you see enough? 0.707 with an angle of minus 15 degrees, and that's the current, the total current that's flowing in the circuit. Now, if you take a look at the problem statement, it asks us to find I of t and lowercase notations of all the voltages. What's the difference? Anyone? They're exactly the same. So I of t, here t is not mentioned, but it's still asking you for voltage across the resistor as a function of time, Vc of t, Vl of t. So if it's lowercase, with or without the time, it is asking you for the time domain expression. If it was uppercase, something similar to this, then it was asking you for the phasor voltages or the phasor current. You can then leave your answer in phasor form. But if it's asking you for the time domain expression, then you have to transform it. You do the inverse transform and leave the final answer in the time domain, which is just one additional step, right? So here I transformed into the time domain becomes 0.707 cos of the original frequency is 500 minus 15t. So the point is that pay attention to the problem statement. Pay attention to what is being asked of you. Otherwise, you end up losing points, even though you had the correct answer. If it asks you for the phasor current I, then you can leave your answer in this form, 0.707 with the angle of minus 15. If it asks you for lowercase I or I of t, then yeah, final answer has to be in this form. Is that clear to everyone? Make sense? Does the method make sense? But the analysis technique, the method is something that you've already done before. It's nothing new. All right, any questions? Any questions at all? Okay, and then to find the voltages, all you're going to do is apply Ohm's law again. So you get volts. And so lowercase vr of t would be 70.7 cos of 500t minus 15 degrees volts. Similarly, VL would be I times ZL. That would be 0.707 times 150. Magnitudes are multiplied. Phase angles are added up. 106.08 And then time domain expression would simply be 106.08 cos of 500t plus 75 degrees. And then similarly, VC and now have minus 15 minus of no plus minus 90. And so that gives me VC of 35.35 cos of 500t minus 105 degrees. Oh, that should be lowercase. Easy enough? Any questions? Yes. You can do so. That's a very good question. It's going to be my next point. VL, inductor voltage from chapter 3, is L di over dt. So if you want to do a bit of mental maths or mental gymnastics, you could take the current expression, which is 0.707 cos of 500t minus 15 degrees, take the derivative of that expression with respect to time, multiply it with the inductance, and you should obtain the exact same answer as here. Yes. Yep. And that's why I love solving with complex numbers. Keeps things a lot simple. And the same thing, if you wanted to find capacitor voltage, we'd have to integrate the current. So if we take the derivative of the current, we get the inductor voltage. If we take the integration, if we integrate the current, we get the capacitor voltage. But you can see why complex number representation is so useful, right? If you have complex circuits, all we have to do is represent everything as a vector. And once you do that, all you have to do is you can apply all the analysis techniques that we learned previously. KCL, KVL, voltage division, current division, mesh current analysis, node voltage analysis, which seems like fun in complex numbers, right? Well, fun for me. So if this was an EE major class, we actually do circuits and we perform circuit analysis of of sinusoidal steady state circuits. Sorry, sinusoidal steady state analysis of circuits using mesh current and node voltage analysis techniques. Non-major class, again, we're just snorkeling. We don't go deep into the material. But the exact same techniques would apply. You can solve all of those circuits using the same techniques. Only the math is now with complex numbers. So as student practice, I will assign you, don't worry, it's not mesh current. You can solve this with another method. Any techniques come to mind? You have a voltage source connected with a series combination of impedances. What happens when you have a voltage across a series connection? Voltage division. So you apply voltage division exactly the same way, and you would be able to obtain VR, VC, and VL the exact same values. You would not have to find the current if you didn't have to. And so VR would be a fraction of VS, and the fraction will be given by R over ZEQ. Again, you can practice this when you're outside of class. It shouldn't take you longer than it takes you to plug this equation into the calculator. Make sense? Right? If you had a parallel connection, if you have a parallel circuit, you could apply current division. It would work exactly the same, no difference. All right, take a look at the voltages, all 4 voltages, and let me know what you see over there. Take a look at the values of the 4 voltages. What do you see? So let's scroll down a bit. What do you see? Absolutely. Vs is only 100 volts. Yet if you look at the inductor voltage, that by itself is more than 100. Then you add the capacitor voltage is 35.35. You add the voltage for the resistor, that exceeds like 200. So if we don't take the phase angles into account, the magnitudes will not sum up to the voltage source Vs. Okay, and that's the main takeaway from here. So KVL will still work if you take the phase angles into account. So if you add up these phasors, VL, VC, I did not add this up, 35 and minus 105. Anyway, add up VL, VC, and then VR, they will add up to Vs, which is 100 with the angle of 30 degrees. And the reason is simple. Capacitors and inductors are polar opposites. They are duals of each other. They are out of phase by 180 if they are sharing the same current. So in this circuit, they actually share the exact same current. What happens is, in an inductor, in a positive half cycle, energy flows in. In a capacitor, in the positive half cycle, the energy actually flows out. In the negative cycle, the exact opposite happens. In the negative cycle of the voltage, the energy flows out of the inductor and into the capacitor. So if you have a capacitor and an inductor in the same circuit, whether in series or parallel, in one half cycle, the energy flows out of the inductor, goes into the capacitor. In the other half cycle, it flows out of the capacitor, goes into the inductor. And it keeps going back and forth. And because of that, you have higher voltages and currents, at least in terms of magnitude, than is the magnitude of the total source voltage. It is also the most important point when we actually begin analysis for AC power. So AC power deals with the reactive power of the inductors and the capacitors. Again, we're not looking at it today. We'll begin that on Wednesday. But the reason we study that is because for an inductor, the energy flows out into the capacitor and out of the capacitor back into the inductor, bouncing back and forth. All right, let's draw the phasor diagram. So phasor diagram is nothing but a graphical representation of the phasors. A phasor is nothing but a vector. What do we need in order to describe a vector? Magnitude and direction, right? So we need the angle that the phasor makes with the real axis, and then we just need the length. So if this was my real axis, first, let's draw VS. VS is at a 30-degree angle with the real axis, right? Plus 30. So plus 30 would be, let's say, somewhere here. Actually, that's more like 40 rather than 30. But let's say maybe here. And again, this is not to scale. This is VS. This is 30 degrees. The current I has minus 15. Excuse me. The current I is minus 15. Remember, this is 0, this is 360. It goes, the phasor is a rotating vector that rotates counterclockwise or anti-clockwise. So positive angles go like this, negative angles go into the fourth quadrant. So minus 15 starts from here, from the real axis into the fourth quadrant. And so minus 15 is somewhere here. And the magnitude of the current is just 0.707 compared to the magnitude of the Vs, the source, which is 100 volts. It is very, very small. So again, I'm going to enlarge it just for effect. Now the current is the same for all components. So I is also IL, IC, and IR. Resistor voltage also has a minus 15 degrees. So it's in the exact same angle along the exact same path. And so resistor voltage is going to be here. And this is the phasor VR minus 15 degrees. Now, we just said this current is also IL, IC, and IR. IC, if you remember, has a minus 90 degrees relationship with the voltage. Sorry, plus 90, right? Eli the Iceman. Capacitor current is always 90 degrees ahead of the voltage. So capacitor voltage will be further 90 degrees behind that current, which we know because it's minus 105 degrees. So it's a minus 105 degrees with respect to the real axis. Does that make sense? That's a lot. That's a lot to think about. But if we just take minus 105, minus 105 is going to be here. So minus 105 with relation to the real axis. And this is VC, right? 105 and 15, 90 degrees between the current and the voltage. The current is ahead, the voltage is behind by 90 degrees. For the inductor, the exact opposite. Inductor voltage is ahead of the current. And so here at plus 75, we have the inductor current VL. That's it. That's our phasor diagram. Because it's a series circuit, the capacitor and inductor share the exact same current, which is I right here. This is minus 90. Capacitor voltage is minus 90 with respect to capacitor current. Inductor voltage, Eli, right, plus 90 with respect to the current I. And because they are in the exact same circuit, that's why they have 180 degrees out of phase relationship. If it was a parallel circuit or anything else other than series, they would not be sharing the same current. Then they would not be out of phase with its, amongst themselves by 180. It would be something else. It would be different. Does that make sense to everyone? But again, phasor diagram without complicating the relationships. First, find the angle. Once you find the angle, you just plot it along that angle line, and then just mark the length. That's it. That's the phasor diagram. And if you wanted to plot KVL, we would be able to plot it by using or taking all of the angles into account. So it'd be VR, then it would be VC, and then it would be VL, and then VS would be satisfied. Without taking the angles into account, the magnitudes would not add up. Okay, any questions? All right, we'll end class here today. We'll pick up here. Well, this is the end of chapter 5. Right, end of chapter 5. We'll go into AC power on Wednesday, which is chapter 5.5. I'm not in my office this afternoon, So I don't have in-person office hours, but I am available via email and Zoom. So if you need to see me, if you need to meet with me, I am available via Zoom. All right.